Mathematics has one rule, and that is make sense. If there was perhaps another rule, which maybe we'll refer to as a suggestion, it's try to be as clear as you can. But within that, there's a lot of flexibility. Some of the notations aren't quite clear what their meaning is, and there's a lot of different ways to express things that aren't always the simplest. But the idea being, all of mathematics comes back to what is the statement that's being said, and how can you rewrite, transform, or adjust your perspective to see that statement in another light that allows more insight to be had. Now, there's not a better example for this creation of representation than perhaps in absolute values. And absolute values, again, are just simply a creation that mathematicians imagined up as trying to fill a void in the logic they had in their mind and what they needed to see happen on the paper. Now, we've seen examples that are just as similar and just as profound. For example, when we first learned about exponents, the idea that you could express repeated multiplication as being just writing a little number in the top right corner is a claim that somebody made at one point as a means of trying to capture these big ideas, trying to express that we want to talk about large repeated multiplication in a very small space, and that we can, if we're careful, use a lot of different rules or discovered patterns to be able to simplify expressions one way or the other. Absolute values do the exact same thing, where there was an idea that somebody wanted to express, and in order to communicate that they were trying to accomplish that idea from a place that made sense, they created their own notation and symbols for the paper that now all across the world we understand as being essential for communicating a lot of algebra. Now, absolute values have the purpose, many of us are told, as to make something positive. And this is true, but it actually had a much deeper and much more profound purpose and has a lot more applications than this. The original reason for using absolute values was to try to capture distance. So, for example, if I wanted to, in my car, keep track of the distance that my car had traveled, in that situation there is no need for positives and negatives. If I travel forward or if I travel backwards, I'm not going to be decreasing the total distance that I had. I'm not going to be coming closer to zero depending on if I move around that number line in a certain direction or another. Instead, we're just trying to combine all of the values in such a way that grows and grows and grows. If anybody's ever seen the movie Ferris Bueller, which if you haven't, you need to go check it out, there's a really famous scene in which Ferris Bueller and his friends take his friend's dad's car and drive it to Chicago and back. And in order to try to get the miles off of the car so they don't get in trouble, they try to drive the car in reverse for a long period of time in an attempt to bring that odometer down. Of course, it doesn't work. Again, being because the car isn't measuring negatives, it's only measuring positive distances. So we've got distance as being a place where absolute values pop up. It also helps out with speed. For example, you'll never see in a car that you are traveling at a negative speed. It only has positive speeds, whether you're going forwards or backwards, north or south. And so all of these ideas of trying to capture distance and speed and making things positives is what absolute values is trying to capture. And it captures it with some very simple notation. We'll take a look at it in just a moment. All right, so let's go ahead and look into our notes. And so we have a little bit here, try to fill out a little bit of what absolute values are used for. They're used for speed, they're used for distance, but also if we want to just talk about it from a place of mathematics, let me show you how we can use it for talking about the distance between two numbers. So for example, if I asked you to please try to find me the distance between the numbers 3 and the number 8, you might try to say that would be then starting at 3 and growing 5 steps towards 8. That would be valid. You're trying to, in that case, figure out what is the number of steps I need to add to 3 in order to get 8. If I instead asked you what's the difference between 8 and 3, how do you go from 8 to 3, you might say, well, if I start at 8 and I go back to 3, that would be taking away 3 from where I'm ending up, and that would be giving me a total of 5. So in that situation, that's where we're solving for our unknown. But if I asked you what's the distance between 3 and 8, and I didn't tell you if we were starting at 8 or starting at 3, I'll show you a really cool way that we can do that. Whether you start at 3 or you start at 8, you can find the distance between two things by subtracting one from the other, and then that's going to be your answer, which in this situation would be 5. So whether you want to find the distance between 8 and 3, or you want to find the distance between 3 and 8, if you use absolute values, you're going to get the exact same answer, which is just a positive 5. Now that's well and good, but what if instead I asked you to find me the distance between the number 54 and the number negative 13. How would you find that distance? You might say that it would just simply be 54 minus 13, but be careful, that would get you something along the lines of that get you 41. And if you imagine starting at 54 and going 41 units back, so you go 53, 52, 51, 50, and you count 41 steps, you're not going to make it all the way there. What's the distance between the two? Well, we can use absolute values to help us. Take one of the numbers, subtract the other number, and I'll use parentheses to show that I'm subtracting this negative number. And if you use your absolute values as a means of talking about distance, you're going to get the total distance. So that would be the absolute value of 54 plus 13, which is going to get you the absolute value of 67, which is just 67. And if you tried it the other way around, you said I wanted to start at my negative 13 and I wanted to take away my 54, you're going to see that you're going to get the exact same idea. So absolute values help us to capture distance between things, and also speed, or pretty much any idea that we would like to try to take negatives out of the pool of correct answers. So let's take a look here. How would we solve a question like 1 minus 3x to the absolute value equals 4? Well, the important way to solve this is to remember what the meaning is. The absolute value takes positives and brings them to positives, and takes negatives and brings them to positives. So we can really quickly recognize that the solutions to this answer would be any time the inside of these absolute values is either going to be 4, because then the absolute value of 4 is 4, or if the inside is negative 4, the absolute values are going to make it a positive 4. So let's just express that in our thoughts. What we can do with our paper here, we can say that this exact expression above is the same thing as saying that 1 minus 3x, the inside of these absolute values, could be either 4, or it could be equal to negative 4. So I'll write that as 1 minus 3x could be equal to negative 4. So it's kind of interesting that we know that having negatives on the inside of absolute values makes them positive. We know positives on the inside of absolute values make them positive. So if we're trying to go in reverse and undo that absolute value, what we're really wanting to do is express two different ideas. And each of these we could solve independently. So now we have 1 minus 3x equals 4. We could subtract 1 from both sides. That would get us negative 3x is equal to 3, which would be x equals negative 1 from doing division of negative 3 on both sides. That's one answer. Or if we subtract 1 from both sides in this situation, we're going to get negative 3x equals negative 5, which means x is equal to 5/3. So there's two different numbers that could actually work for this situation. X equals negative 1 and x equals 5/3. Let's take a moment and let's try those back just to check our work. So we'll change our pen color. And let's go ahead and make it into, we'll do orange this time. So now we've got orange, and I want to show you that if we take x equals negative 1 and put it in, we're going to get the solution to our set. We have 1 minus 3 times a negative 1, and we're putting that in absolute values. That's going to be the same thing as absolute value of 1, and then negative 3 times negative 1 gets me a positive 3. And so 1 plus 3 is equal to 4, and the absolute value of 4 is 4. So there we are. That's a good check. Let's do the exact same thing with the other way. So now I've got 1 minus 3, and then 3 is going to be times 5/3. And if I wanted to simplify that, that would be absolute value of 1 minus, and then the 3 times 5/3 would be 5. And sure enough, that would get me the absolute value of negative 4, which gets me 4. So I have two different solutions that both work for this initial expression. So this absolute value kind of allows us to split off into two different ideas, both of which are as valid as the other. So I'm going to leave this one for you. This is a you try problem. Try to solve the exact same question we have below. Notice it's a little bit larger, but this isn't anything to be scared about. If you're trying to get that absolute value, think about the first few things you can do. Perhaps the first thing you want to do is subtract 5 from both sides. And then after you subtract 5 from both sides, you could divide both sides by negative 2. After you do both of those things, you're going to have the exact same structure of a problem that we just handled. So try both of those on your own and then come back to this video. So let's take a look at a little bit of a harder problem. This one here has a denominator as fractions. Does that change anything? Well, what do we know? We know that the inside of the absolute value can be either positive 11 or it can be negative 11. So we could write that as saying 5x minus 1 divided by x plus 3 is equal to 11, and 5x minus 1 divided by x plus 3 is equal to a negative 11. both of these could be true and the original statement would be true. So we're going to say that we have almost 2 problems we need to solve for each one of these. How could we solve something? Well, I have fractions. Now take a moment and recall that if you ever have a situation in math where you're frustrated, you always have the ability to transform it, just so long as you can identify exactly where that frustration is coming from and how it might look a little bit differently. Right now, my frustration that I'm looking at this is I have a fraction and I'm saying that's equal to 11. And in fact, it's really annoying that in the fraction, there's variables on the numerator and there's variables on the denominator. Well, I might ask myself, how is it that I cancel fractions? Forget about the variables. Variables just mean that there's numbers on the top and numbers on the bottom. How do you get rid of fractions? Well, for example, if I wanted to say I want to get rid of the fraction 1/3, I would get rid of it by multiplying by 3, and then balancing things out and making sure that I hadn't changed the meaning. Even if I had the fraction 2/3, the 2 really isn't what's bothering me. It's the divided by 3. It's the denominator there, which again I could get rid of by multiplying by 3, and then that would get me 2, which to me looks a lot more friendly, and here I would get 1, which looks much more friendly. So the same logic is going to apply when we're dealing with fractions that have variables in it. Just focus on what's annoying you and find a way to get rid of it. So here I want to get rid of the x plus 3 in the denominator. Let's multiply by the denominator the same way that I did with these 2 numbers. So now I'm going to multiply the left-hand side by x plus 3, and that's going to be 5x minus 1. And I'm going to multiply the right-hand side by x plus 3. That's going to be 11 times x plus 3. Now notice here that because we did have something in the denominator, we multiplied by a variable thing, we need to be careful about making sure that the denominator cannot be equal to 0. So if x is equal to a -3, this whole thing throws apart. So we can say x cannot be equal to -3, because if it was, we'd be dividing by 0, things wouldn't make sense, and everything that we're doing moving forward wouldn't work. So we're going to make a little note here that x cannot equal -3. But besides x equals -3, all the rest of this remains true. This would be 5x minus 1 equals 11x plus 3. And we're back to the same kind of linear problem that you're so familiar with. So I'm going to leave it to you to solve the rest of this problem. Figure out what one of your x solutions would be. Check and make sure it's not equal to -3, but if you solve this all the way down and you get a number, and that number is not equal to -3, you found one solution that works for our original problem. Over here on the right-hand side, we've got, again, 5x minus 1, but now we've got equals a -11 times x plus 3. So when you multiply this through, you're going to have 5x minus 1 is equal to -11x minus 33. And so here we again have a linear problem that you'll be able to solve out the same way that we've done in all of our past sections. So again, I'm going to leave this to you. This will get you another solution for x. And now you've got one solution after you finish this problem. Make sure you box it to represent it. And you'll have another solution after you finish this one. And those will be your 2 solutions for this problem. Kind of cool that you've got almost this very intimidating looking problem that has division and everything else in it, but really all you need to talk about is what does it mean to be on the inside of absolute values. Okay, so let's take a look at some of these ones here. These ones here look like they may be a little challenging because now I've got squares, I've got quadratics. But again, there's no difference. I've got 2 problems. I have x squared minus x minus 8 could be equal to 4. And then I have the exact same thing, x squared minus x minus 8 could be equal to -4. Now we just need to factor this out. Remember that we can always factor out. We imagine our little rectangle. I'm going to have an x squared for sure. I'm going to have, let's see, -8 of these units. And so that's going to be, let's see, I've got -8 of these units. 1, 2, 3, maybe 4, 5, 6, 7, and 8. And so I need to find some way to be able to rearrange these ones if it's going to work out into a nice polynomial. Here, I'm not really seeing that there's going to be. I can't think of 2 numbers that multiply to 8 that then add to -x. Oh, but remember, we now have a shortcut from the last couple sections that we developed. We invented/discovered the quadratic formula. We can use the quadratic formula, but only if I have a quadratic equal to 0. So let's just take one moment of work. We'll say x squared minus x, and then I'm going to subtract 4 from both sides. So I'm going to say -12 equals 0. And then over here, I'll say, because remember, this is an OR, we've got 2 possible solutions that can be on the inside, x squared minus x, and then I'm going to add 4 to both sides. So that'd be -8 plus 4 would be a -4. So I've got -4 equals 0. And I can throw both of these in the quadratic formula and just be done. So as long as I remember there's a little bit of a rhyme. So it's opposite of b which is opposite of the number that's in front of the linear component. So opposite of -1, opposite of b, plus or minus the square root of b squared would be -1 squared, b squared minus 4 times a times c, 4ac, all over 2a. So it'll be over 2 times 1. It goes to that all around the mulberry bush theme. Okay, so now we've got, on the other one though, so we've got the opposite of b, so that'd be the opposite of -1, plus or minus the square root of b squared, that'd be -1 squared will be 1, b squared minus 4 times a times c would be times 1 times -4, so actually that'll be just times -4 output, all over 2a, so all over 2a would be all over 2 times 1. And from here we can just simplify this out. This is what x is equal to, since I started off with a polynomial equaling 0. So a little bit of simplification, -1 gets me a +1, plus or minus the square root of -1 squared gets me 1, minus 4 times 1 times -12, that's going to be plus 48, all over 2. So that's 1 plus or minus the square root of 49, all over 2. Okay, so that's going to be one of our solutions. Let me make sure that I clean that up a little bit. So all over 49. And on the other one, we've got x is equal to 1 plus or minus the square root of positive 1 plus 16, so that'd be a square root of 17, all over 2. Now we can simplify one of these, but we can't simplify the other. So I'm seeing that on the left-hand side we have x equals, and I could do 1 plus or minus square root of 49 would be 7 over 2, and we could simplify that up a little bit more. So I have 1 plus 7 over 2, so that'd be 8 over 2 is 4, or I could do 1 minus 7, which would be -6 over 2, would be -3. So that's two solutions that happen from the left-hand side alone. On the right-hand side, I have plus or minus root 17, and because 17 is a prime number, there's not any numbers that multiply into it, I can't factor that down and make it appear more simply. So I'm going to have to leave that in its kind of undone expression. But notice here, it's kind of interesting. We have 4 different solutions that we've created. We have this one, which is 1 plus root 17 over 2, or 1 minus root 17 over 2. Both of those would be solutions. And then we also have x equals positive 4 and x equals -3. And if any of those got thrown into here, we would end up getting a situation where I am in fact equaling 4. Kind of crazy that you have one expression could have now 4 different solutions, depending on which of them you're plugging into this original structure. Now, this looks like an awfully clean number, and so a nice way to kind of check your math in a subtle way is to go back through and to say, is there a way I could have recognized this situation earlier, the solution earlier? And sure enough, right here, perhaps you already did, but you can recognize that instead of choosing to use the quadratic formula like we did, we could have saved ourselves a lot of time if we recognized that x squared minus x minus 12 factors very easily into x minus 4 and x plus 3. And since the original, or the line before is equal to 0, this is still equaling 0, which means that the solutions would be x equals 4 and x equals -3. The exact same solutions we came through when we did the quadratic formula. So quadratic formula works out very well when you don't know what else to do, but you're trying to solve a quadratic equals 0. If, however, you're able to maintain kind of that awareness, which it escaped me this time, you can sometimes save yourself a lot of trouble by being able to recognize those nice clean factors using integers and whole numbers. Now on the very next problem, this one here I'm going to leave for you. Again, it looks like it could be quite intimidating. I'm going to get you started, but you're going to help kind of to finish it to the end. Keep in mind the absolute values now are no longer scary. All the absolute values say is that the inside is going to be equal to a positive version and equal to a negative version in order to account for all the different ways that we could be equal. So I have square root of 2x plus 9 minus x is equal to 3, and then I could also have another version where it's -3, so it'd be square root of 2x plus 9 minus x equals a -3. There we are. Now let's see what else we could do. I want to get rid of the square root. The square root's what's really annoying me. I'm focusing it as my center of frustration. I would normally get rid of it by trying to square both sides. If I do that, I'm going to have to FOIL on the left, and it's going to get quite crazy. So at this point, now that we've recognized our frustration, we might need to take a step back and be a little bit more strategic about how we handle it. I'm going to show you what I ended up doing after I played with this for a little bit. What if instead we wrote 2x plus 9, the square root of 2x plus 9, and then we got it alone. So now on the other side I have 3 plus x. I'll let you go ahead and do the exact same follow along with this other solution, but I'm just going to show you the strategy that I came up with. To get rid of the square root, I squared both sides now, and now I was able to get something that looks a lot nicer. I've got 2x plus 9, because the square and the square root cancel, and on the right hand side, I would need to eventually make sure that I squared this fully, and it's going to involve some foiling, some distribution, but overall it's nothing I haven't seen before. And then of course I could work this to the end, but again, I'm going to leave that for you. This is a you try problem. Now, last class we had been talking about inequalities, and so if you're behaving as a curious mathematician would, the first question you'd want to ask is, how does this new idea, this new absolute value fit into the family of math that we've been growing together? How does it work with these less than or equal to, these greater than or equal to signs? Is it as simple as making things into negatives and positives? Is there perhaps a chance that because it's negative and positive, you need to flip the sign around? So let's take a look at that one. Let's be curious mathematicians and make sure that as we're developing math together, we aren't creating something that's going to be a conflict. So, what numbers make the following statement true if I said the absolute value of x has to be equal to -3? Well, that's a little bit of a contradiction, isn't it? Didn't we just say that the absolute value of x is supposed to be taking numbers and turning them positive? If that's what it means, it's supposed to be giving us distances, it's supposed to be giving us speeds, and that negatives aren't supposed to be playing a role? Well, then it's a counterintuitive for us to say that the absolute value of x is equal to -3. That doesn't work. So this, it's got to have no valid solutions. We'll say no solution. And in fact, we could think to ourselves that if the absolute value of x was ever being told to be negative, that's just a situation that can't happen. There's not a solution for that under the paradigm of math that we've created together. What if I said that the absolute value of x has to be less than -3? Well, the only values less than -3 would be negative values. Again, I don't think that I could have an absolute value that would be less than -3, so I think I'm going to say that this has no solution. Okay, absolute value of x is greater than 3. Now that one's interesting. What values could it be that would be greater than 3? Well, that means that the inside of here, could it be the number 3? It could not be the number 3. Could it be the number 4? It could be the number 4. It could be the number 5. It could be the number 5. I think we're going to need our number line here to see if we can describe everything that would work. I know that we have 3 here. We said 3 was a number that did not work, but 4 did. I could imagine that 3.5 would work, and 3.1 would work, so I think all numbers just to the right of 3 work all the way up until forever. So I'm going to describe that with my picture here. Okay, so I've got everything over there works. Is that all? Well, what if there were some negative numbers I put in? Could I put in -1, for example? -1 absolute value would be 1, and 1, okay, that wouldn't be big enough. What if I tried -14? -14, if I put it into absolute values, would be +14, and that'd be bigger than 3, so 14's going to work, or -14's going to work. What do we think would be the lowest number that would work? -3, would -3 work? -3 made positive would be 3, and 3 is not greater than 3. Okay, so that's not going to work. -3 is not going to work. -4, though, would, because if I took the negative part off of that, I would be big enough. And then -3.5 would have the same logic as working. Okay, so really what we're talking about is, again, -3 is my reference point, and all of these numbers over here that are further away are going to work. Oh, and it's at this point that we can recognize and incorporate in what the meaning is of absolute value. Absolute value is talking about the distance something is away from 0. That's really what it's talking about. So here, when I talk about all of the x values such that their distance away from 0 is bigger than 3, then really what I'm talking about is all numbers over here that are to the left or to the negative version that are at least 3 away, and over here, or I should say more than 3 away, and over here to the right or the positive version, everything that's 3 or more units away. So the solution here would be all values that are x less than -3, or x values that are greater than 3. So again, I've almost got 2 piles of numbers that all work. Kind of crazy that that's working. So I'm going to give you a moment here to think through what these patterns will be. And notice that these patterns have a little bit different. So the first one says, if U is an algebraic expression, so algebraic expression is just simply anything that has variables, multiplication, division, squares, square roots, what we've talked about. So U is any kind of expression that I could create, as big and complicated or as small and simple as I'd like. And C is a real number such that C is greater than 0. What does that mean? That means that C is just any number that is positive. Okay, so it's a number that's positive, but keep in mind positive means not 0. So it's a number that's not 0 and positive. Okay, what can we say? The absolute value of that expression is equal to C is the same as saying what? Well, I'll give you an example, but I'll let you write it in for your notes here. That could be something like, what would it mean to say that if I had X, or a whole bunch of other stuff like X, that absolute value of X is equal to a positive number, let's say 4.8. What could X be? And I want you to write that in right over here. X could be, or, all right. What if I said instead that I had some kind of expression where it's U, the absolute value of U is less than C. So now I'm going to try, and it's any algebraic expression, remember. So maybe I'll say like square root of X, or I had the X squared, or I had X to the 14th, or I had 2X plus 5, anything I wanted. But what I'm saying is I have the absolute value of something or other here, and I'm saying that it is less than some number. Again, maybe we'll use 4.8. What are two different ways that you could express this? Could you express this as maybe something like this? This one happened with the greater than symbol. So we could do the last one together. We could say that absolute value of U is greater than C is equivalent to saying that U is either less than negative C or U is greater than a positive C. Notice for a moment what exactly I did here. I'm just generalizing the exact same things we learned from above. U, I went up here and I referenced, I said I have X, some kind of algebraic expression, something on the inside. Something on the inside, absolute valued greater than 3 means that the inside expression, whatever the inside expression was, whether it's U, whether it's something longer, the entire inside has to be at least, or has to be more than 3 units away from 0. So that means that it has to be smaller than negative C, in other words, further negative than negative C, or it has to be greater than C, in other words, further positive than positive C. So this is just two ways for us to kind of generalize what we have figured out by just playing around with what it means to be an absolute value. So see if you can write similar expressions for numbers 1 and 2 above. All right, let's see how we could use this. Now that we've discovered our shortcut, now that we've found a rule that we can generalize, we found a pattern that we can play with, what exactly can we put this to use for? So solve the absolute value of 5x plus 1 is greater than 3. What this means is that the inside expression, this 5x plus 1, has to give me a number, and that number has to be more than 3 units away from 0. Okay. So that means that 5x plus 1 has to be further to the positive than 3, or 5x plus 1 has to be further to the negative than negative 3. Kind of cool. Well, here don't we have everything we need to solve on down then? That'd be 5x has to be, we could subtract 1 from both sides, that would be, has to be greater than 2, and that means then x has to be greater than 2/5. That works out just fine. We could say, or, over here we've got 5x, and then we'll subtract 1 from both sides, that's going to be negative 4, and then I've got x is less than negative 4 over 5. That would work out just fine. So on a number line, what we've created is we've said that everything on the inside here, all this moving, shifting, expanding, contracting, is really saying that I have piles of numbers that work so long as everything to the left-hand side of negative 4/5 and everything to the right-hand side of 2/5, if I am in either of those categories, I am a number that makes my original thing true. So all of that is full of solutions of numbers that make my original statement true. So I'd like you to try the exact same thing with this one. Notice that again, there's going to be some simplifying that needs to happen. You'll have to figure out what you'd like to get rid of first. For example, I have a 7 over here before I can just get at the absolute value, and I have a negative 2 here that's in the way of getting at the absolute value. Get rid of those first. But then after you do, you should have an absolute value, and you'll want to figure out how is it that I'll be able to rearrange this entire pattern. Is it going to work where I need to have this rule, or perhaps this rule? Kind of crazy. On the next problem, I'm actually going to make this one a little bit more difficult for all of us, and then I'll simplify this one out. So let's imagine now that I have less than or equal to -4. So we're going to make this one a little bit harder. So solve the absolute value of x plus 6 has to be less than or equal to -4. That's not going to work, is it? I can't have an absolute value that's less than or equal to -4. Well, that was a pretty easy one. That has no solutions. But maybe that was, let's play. We're here playing. So let's imagine what would have happened if that wasn't the case. So let's have x plus 6 absolute value, and let's set up a new problem for ourselves. Let's say it's less than or equal to 4. What does that mean? Well, that means that all of the numbers on the inside here, x plus 6, whatever comes out from that, has to be closer to 0, or at least 4 units away from 0. So what I'm saying here is that on a number line, I'm looking for all of the numbers that are less than or equal to 4 units away. So that would be everything between +4 and -4. Because it's less than or equal to, I've got a little circle dot here. And so I want everything that's on the inside here. Okay, how could I express everything that's on the inside here as being a solution? All of this is my solutions for x plus 6. X plus 6, if it's anything in here, then it's definitely going to be 4 units or less away from 0. Well, I'll show you how. We could do it as x plus 6, and I need it to be simultaneously less than or equal to 4, and greater than or equal to -4. So we have our compound inequalities from before. This thing is popping up again. How can we get at x? Well, we could just take away 6 from everything if we wanted. That'd be x less than or equal to 4 minus 6 would be -2. And on the left-hand side, I would be taking away 6, so that would be -10. And I want you to take a moment and I want you to try that out. Choose any number you'd like in here, maybe -5, maybe -8, and I want you to try to throw it into this equation. You tell me if it works. I'll choose my own. I'll choose -3. So if I put -3 in here, and -3 plus 6 would be a +3, and absolute value of +3 is 3, and it is in fact less than or equal to 4. So we've got an entire range of solutions, but this one doesn't go on forever. This one is almost trapped. So we've got the opposite. Now, this is the first time that we've explored one of these trapped examples, and so before we're trying to figure out a rule for how to handle situations like this, you might want to take a look back at that one, because the rule that goes along with 2 is going to follow the exact same pattern as what we just played with in this last example. When you have the absolute value less than c, what that means is that you're looking for all of the times when the u expression, whatever it is closer to 0 than at least c units. So you're going to want something along the lines of u is less than and greater than, and I'll allow you to kind of guess what it is that goes right here. So the idea with today is that whenever you're working with an idea, you're playing around with an idea of whether it's absolute values, whether it's exponents, whether it's trying to talk about set notation, anything that you want to play with, you can. But when you introduce a new idea and you'd like to say, I'm going to want to talk about just making everything positive, you have to ripple through and say, what are the consequences of creating this new math? What are all the different ways we could play with it? What are all the different shortcuts we can examine with it? And are there any times when we get into a conflict, like when we say absolute values are equal to negative numbers? How do we answer that? Is there a way to answer that? And you start to realize that coming up with any form of pattern of logic is fair game, but that doesn't necessarily mean that you're always going to be able to put down something that has an answer.